lovely people. How are you doing? Okay, it seems like you're already relaxed and you know you're back in normal routine in school. Anyway, we're going to carry on this online. And as I said, if you want to see me recording these lessons, you want to be here and ask me the question, that's no problem. Just let me know. Okay, I just need to know about that so I can organize. I can do it when you don't have classes. Otherwise, I often do it during the morning. Anyway, and also to remind you that Wednesday is our day where you're going to come up and ask questions, right? So we're not having live lessons anymore because you guys are here. Wednesday is dedicated clinic for you guys. Okay. So today we learn how to differentiate without using the definition. Last lesson we learned what differentiation means. Okay, it's basically the gradient, the instantaneous gradient. Okay, it's the delta y divided by delta x, taking in the limit where delta x is tiny. Okay, but you can, and we learn how to calculate derivatives of functions using that definition. But you could see it took a long time. So probably the main thing we're going to do today is we're going to learn a few tools that allow us to differentiate function without using the definition. You still need to know how to do it using the definition, but for the more complicated function, it will take too long, and then we're just using the rules we're going to learn today. Okay? So before we get to that, there's going to be a few other things we're going to do. We just need to talk about which functions are differentiable. Okay, not all functions we can differentiate in every moment. Okay, and actually our next lesson, which is probably only going to happen next week. I think this week is going to just really have one lesson because it's going to come on one. But anyway, next week we're going to talk more with a little bit more depth into which functions are differentiable or not. But I'm just going along with the book, and they mention it here. So for a function to be differentiable, it really needs to be continuous. Okay? Well, yes, let's start with this. Now, we know continuous functions are one where you can just, if you have a little person walking on the graph, you can just, with tiny little feet, it can walk. Okay, there's no jumps. Okay, so in other words, when we have jump discontinuities like here, or what we really call infinite continuities, which the book calls it also jump discontinuity, we definitely can't differentiate in that point because what is the derivative? What is the differentiation? It's basically the limit of fx plus h minus fx divided by h when h approaches 0. Now, if you look at a point from here to there, okay, I can still take an h, tiny little h, okay? But the difference between f of x plus h and f of x there's a finite difference, okay? It's not tiny, it's not almost 0. It could be 1 or 2, okay? In this case, in fact, it's infinity, okay? Think about the difference in the y's between a point which is just after the 0 and a point just below the 0, before the 0, okay? It's going to be infinite. Here it might be 5, but 5 divided by 0 or infinite divided by 0 is definitely infinite. So there is no derivative in these points. Now, these kind of continuity, we call them removable discontinuity, we can find a limit. We can find a limit of that limit. So, we'll talk about it more in next week's lessons, but removable discontinuity depends how strict you are in maths, okay? From my perspective as a physicist, I would say, yes, you can find a limit, you can find a derivative, because you can find that limit, okay? But if I'm a bit more strictly mathematical speaking, if the function is not defined here, then we probably can't. So, in other words, don't worry about it, because we're not as strict in high school. So, you can find a derivative for that. Right, let's move on to our first proper rule. Okay, so what we're going to do now, we're going to start develop tools for us to be able to come up with the derivative of function without going through this whole process of definition. Okay, so the first one to look at is a horizontal constant. Okay, fx equal, let's say, 3. Now, if you just look at the picture, you remember that the derivative, okay, the derivative of x is basically the gradient of x, of the f. Okay? The gradient here everywhere is 0. Okay? The gradient everywhere is 0. So there's no steepness. It's not up and not down, okay? Now you can also look at it in terms of the definition, okay? What did we say the definition of the derivative is the change in y divided by a small change in x. But now there is no change in y, okay? F for x of every x is always 3. So that's going to be 3, and that's going to be 3. 3 minus 3 is 0. So it's always going to be 0. Okay, so that's the first step. Now the next one, okay, let's move to another example. Let's say we have a straight line, okay? So let's say something like this, okay? This, how are we going to write that function? F of x is equal mx plus n. Okay? Y equal mx plus n. Okay? Now already here, okay, I'm pretty sure that by grade 11 you know what the gradient is, okay? Okay? We'll call that, let's just call it g of x. If this was f of x, let's call that g of x. Okay? What will be the derivative of g of x? Okay? Right? You should know that already. The gradient is simply your m, isn't it? That coefficient of x. Okay? So we've already looked at two kinds of function. One is constant and the other one is a straight line. And we can figure out what the derivative of both of them without going to the definition. Now I will make another recording of another lesson where I'm going to prove a whole bunch of stuff. So here I'm giving you some tools and I'm not really proving them mathematically. I will give you a whole separate lesson where I'm going to prove it. Yeah, so let's not mix them together. Right, I'll pause now. Okay, just before I go for the example, for the next rule, let's just go through an example. So let's say we have, let's say this is minus x plus 3. Okay, so let's just take a specific example. That's the line that we have here. In this case, the derivative, okay, is going to be minus 1. Right? It's the number in front of the x. If there's no number, it's just minus. That means it's really minus 1. Okay. Right. Now let's move on to another rule. Okay, so here's a really important rule, okay? We'll talk to the rule in a second. Let's take a parabola, quadratic equation. F of x equal x squared. I'm just going to tell you that now. I will prove that to you later. But the derivative of that is going to be 2x. Okay? I'm just going to give you a few examples and then maybe we can see the rule together. If, however, we're working, let's say, with another kind of parabola, which is 3x squared, then I'm just telling you now, okay, I'm not explaining why, but you can tell that the derivative is going to be 6x. Okay? Maybe you're starting to see some kind of rule, maybe. If I ever have a cubic function, let's say minus 2x cubed, then the derivative is going to be minus 6x squared. Okay? What is the rule here? Okay? If you've got a function which is x to the power of m, let's say, with a coefficient of a. So a times x to the power of m. So it could be 5x to the power of 6 minus 3x to the power of 10. Okay? Then the rule is that what you're going to do is you're going to take that n. Okay? And you time it by the a, so it's going to be NA. Okay, these are numbers, right? It'll be NA. Then you still have that x, but the power now is n minus 1. Okay? Let's just see that this rule, that's how I used it. Okay, so what did I do here? I said, okay, I took the 2 here. Okay, that was the n. I timed it by 1. I didn't have anything. 2x. And now x to the power of 2 minus 1, which is just x, so it's 2x. 3x squared, I took the 2, timed it by the 3, I got 6. And now it's x to the power, again, 2 minus 1 is just x. I took the 3, timed by minus 2, I got minus 6x. And then I did 3 minus 1, okay? The power, the exponent always goes down 1, okay? So it's minus 6x squared, okay? Let's do another one, big one. So let's say I have y equal minus 5 over 2 x power 8. Okay? So what I'm going to do, I'll take the 8 times it by minus 5 over 2, which is minus 20 if I'm not mistaken, right? 8 over 2 is 4, so minus 20. X to the power 7, it just goes down 1. Okay? Right, pause you here, let's see where we're going next. Okay, just a small correction. I just realized I made some big mistakes. So I wrote, it was written here, but I wrote if y is equal minus 5 over 2x power 8, then I wrote the derivative is minus 20x power 7. It's true, but the way I wrote it is obviously wrong. I shouldn't write that equal there, because obviously these things are not equal, okay? The derivative of y with respect to x, dy to dx, is going to be minus 20x power 7. Okay, so that was a big mistake that I've just written on the board. Right, okay, let's move on to something like this. Okay. So let's say, hang on, let's just look at stuff that we've done before, okay? So we've just, before this rule, okay, which I wrote in here, I wrote this rule, we looked at these two equations. Let's say f of x equal 3. Let's just look at this, okay? So let's look at f of x equal mx plus n, okay? No, I can't do that yet. Sorry guys, I need to be a little bit patient. I'll come back, I'll prove that to you in a minute. Oh, sorry about that, okay? What we're going to do now is we're going to look at a function like this. F of x equal 2 over x cubed, okay? Now, this is also some kind of polynomial. How do I use this rule? Because this rule tells me, all right, take the number, which is the power of the x, times it by 8. Okay, but now I've got this at the bottom. So how does that work? Okay, it's not written like that. How can I make the x cubed to be on top so I could use that? And you know how to do it. Okay, this is equal to 2x power minus 3, right? That's how I lift them up. And now I can use exactly the same rule as I just had here. So df of dx, and I'll show you another notation here. Sorry to crowd, but there's a law of definition of how to write the derivative. I can write it as df to dx. I can write it f the line x. If I have it in terms of y, dy to dx, and I'm going to show you another way of doing it. Okay, dx of fx. Okay, and usually we write it like that. So it's just exactly the same thing. This is basically like that. Okay? When we use this, we call that operator. It tells you basically take that function and do derivative of x. We normally don't use it in this situation. We'll use it, I'll show you later in when we're going to use it. But I want to already introduce you to it. But it means the same thing. So that's going to be, okay, what I'm going to do is take the exponent here, okay, just like I took the n, multiplied by a, so it's going to be minus 6, and then x to the power, and this needs to go down, n minus 1. So minus 3 minus 1 is minus 4. Okay? And then there's actually nothing wrong with leaving it like that, but in a question maybe you'll be asked to write as a positive exponent, and then you can transfer it back to this. Okay? So what you can see is that from x cubed at the bottom, it went down to x power 4. Just went down. Okay? Right. What about if I had f of x equal minus 3 square root x? Okay? What do we do then? Okay? Again, how can I use this rule? So again, you need to remember that the square root of x, okay, you can write it as x power half. Okay? You've learned that, I'm pretty sure. Okay? Square root of x is the same as x power half. And now I can use that, this rule, okay? So, let's just call it y. Just change it every time, okay? So, dy to dx is going to be minus 3 times a half, okay? X. And now I need to do half minus 1. So, it's going to be minus a half, okay? So, that's going to be, this is 3 times, okay? It's not half. So, that's going to be minus 3 over 2. And if I want, I can leave it at x power minus half. I personally will just put it in a square root x, okay? Right? Or take another step. Let's do it in 2 steps. So because it's minus half, I'll write it as x power half now at the bottom in the denominator. And then I'll write again minus 3 over 2 square root x. Mathematically, obviously they're all the same. There's nothing wrong. Okay? It's nicer to see it like this, but sometimes it's actually better to keep it like that. Okay, right, let's pause here. We're not finished yet. Okay, so now we almost ready to deal with polynomial or any kind of function. Let's say I have f of x equal 3x squared plus 2x plus square root x plus 2x cubed. I'm just going to change that, let's say, to h of x. Okay. Now, how do I do that? Because so far I know how to deal with that. I know how to deal with that function. I know how to deal with that, and I know how to deal with that. But I don't know what do you do when you add them together? So here I'm going to introduce you to a rule which is very intuitive, and I think it'll be easy for you to accept it. If I have a function that is made out of a sum function, okay, we can think about that function is made out of this function plus that function, but each one of them is a separate function. So if I add them all up, okay, do you know, I'm just going to make it a little bit easier for you. Let's just think about that, okay? So we can call this f of x, and we can call this g of x. So h is made out of f plus g. Now the question is, let's say now we want to find out what is d of h of x. dx. I want to know that. So what this rule tells me, that if h, the function h, is equal to the function f plus the function g, okay, this is f, this is g, then what I have to do is, what do you reckon? You would have guessed it. Differentiate f, differentiate g, and add the derivative, okay? Mathematically, we're going to write it like this. You're going to say, okay, differentiate f of x, okay? Differentiate g of x, okay? We usually put these square out of brackets, and then add the derivative. Not a problem, okay? What are we going to do now? Okay, we're going to find the derivative of 3x squared. Okay, so I'm going to write now dh of x dx. Okay? You can see one of the difference between the way the notation here. When I write the little d, not the big D, I have to do dh of x to dx. But if I use the capital D, I don't need to write divide by dx. It means the same thing. Okay? When are we using that? We're using that when we do the derivative on more than one function. That's how we usually use it. Okay. So dh of dx will be the derivative of f, which is 6x, plus the derivative of 2x, which is 2. And that's the answer. Easy, isn't it? Let's look at another example. I'll just use one of them. Okay, so we have, let's call it y equal, running out of, okay. Y equal 3 over x plus square root x. Okay? And I want to find the derivative of that. So the first thing to do is really to write it in a way that I can, in this form. Okay? I don't want to have square roots. I don't want to have x at the bottom. So I'm going to write this 3 times x to the power minus 1 plus x to the power of half. Okay? Now I wrote it in a way that I can use this this rule. Okay? So now I can see that y is actually made out of two functions. And if I want to find out the derivative of y, dy to dx, I'm going to do the derivative of that, do the derivative of that, add them together. So what's the derivative of that? Okay, I take minus 1 times 3, so it's minus 3x. And I don't forget, I have to take minus 1 down 1. So minus 1 is minus 2. Plus half x, half minus 1, minus half. Now, mathematically speaking, this is fine. You can leave it like that. But in high school, we kind of don't like having negative exponents for some reason. So we write it as minus 3 over x squared plus 1 over 2. That's that half. And if you don't mind, instead of writing x power half, I'm straight away going to write square root of x. But now it's at the bottom. X power minus half, it's square root of x because it's minus at the bottom. Right, you guys now, if I were you, what I would do is just do exercise 5.3, do as much as you can of it, and then listen to my video later. In my second video, I'm going to give you proofs. I'm going to prove to you for two things, maybe a few more things. But first of all, I'll prove to you why you can use that rule, okay? Why you can do the derivative of y by multiplying, max n minus 1. And the second thing, I will prove that to you this, okay? That the derivative of some function will be the sum of the derivative of each function. I don't know if you understood what I'm saying now. I'll try and explain, okay? The derivative of a sum of function is basically the sum of the derivative of each function. Okay? I will prove those two things to you and a couple more things. Enjoy. Bye-bye.